So we're going to get started this week, and I just want to go over some of the stuff that's happening this week so that you see it and we're all on the same page. I guess the big thing to take note of today is the quiz. So quiz number 2. And I have, before you take that quiz, I have this section here. Before you begin quiz number 2, read that. So the quiz uses the tables for, I can't remember, for R134A, which is a refrigerant. So you want to make sure you have those available to you. They're at the bottom here of the Moodle page. If you don't have your book, you scroll all the way to the bottom. Thermodynamic tables, R134A right at the bottom. So pull those up, have those ready so you're not scrambling to try to find those while you're doing the quiz. The other thing to note, this quiz, for the last 2 questions especially, if you get the answer wrong, scan your work and email it to me so that I can see the work that you did. Otherwise, it's more challenging for me to try to back out exactly what you did, especially if you made some really minor error, like you tried to add 2 numbers and you just plugged them into your calculator wrong. Obviously, that's not a big error. You're not going to lose a lot of points for that. But if I can't figure out what you did, then it's hard for me to say, oh, it was just a calculator mistake. So if you get a perfect score on it, that's great. Then you don't need to. But if you don't, scan your work and email it to me when you're done with taking the quiz. So that's I think the other bullet point. I guess the last one is this is a 30-minute time limit. My guess is that this will be somewhere, I don't know, maybe 15 to 20 minutes, but maybe it will take you the full 30 minutes. That's the time you have. But because it's timed, make sure you get out the tables. You got to kind of set off that block of time so that you can get through the whole thing. And that's by midnight tonight. Okay. If you have any questions, if you have a problem, if like you're in the middle of it and your dog needs to go to the emergency vet, like shoot me an email. Right? We can always work through stuff by that, but I can't if you don't let me know. So that's the Moodle stuff going on. The other stuff going on, yes, there are 2 different lecture videos and then kind of like a participation thing, which is kind of a new, and you'll find it enjoyable version of the STEAM tables. It's a digital version, so you don't have to look everything up quite so much anymore. So that's a nice version. That's this software Cat 3. Hopefully you can get it installed on your computer. If not, I don't know how it works on Macs. I'm not 100% sure. I think people have had issues before, but I'm not sure if people have been able to work through those or not. So you may have some issue, I guess, if you have a Mac. Otherwise, I think it should work fine. And then the second video is another example, an example problem there that's like working through a worksheet. So make sure you print that out while you're going through the video so that you have something to follow along with. Okay. So I think, oh man. So I think those are the main things that are happening. Quiz today, I guess, is the biggest one to make sure you have on your calendar for some time today. So what we talked about last class and in the videos associated with that, we started talking about this thing called entropy. And we kind of avoided too much definition along with that as to what entropy is, because I think going too deep into that can make things just more confusing. So entropy, we can think of it as a way to quantify the second law. Okay, and if rather than a word definition, if we want a mathematical definition of entropy, our mathematical definition was this, that the heat transfer for a reversible process, right? This is the reversible heat transfer, Q sub reversible, is equal to the integral of T ds, or we can write it that ds equals Q dq reversible over temperature. And this is maybe if you want to try to get some sort of conceptual framework around things, this is probably the one that we can think of, and we'll continue to talk about. So if you think of it, we're thinking of this hypothetical reversible process, a hypothetical reversible heat transfer. And basically, if we move heat from one space to another, that would be our dq. If we move heat from one space to another at a certain temperature, that causes an increase in entropy. So heat moving from point A to point B causes an increase in entropy. That's kind of what this definition looks at. But it's a little bit, I don't know, it's a little bit weird, and I guess just be okay sitting with that. Again, entropy is a concept that we will continue to revisit. I think the easiest way for you all to think about it at this point is this top one. This concept, it's a way for us to put real numbers to the second law of thermodynamics. So let's look a little bit at what that looks like. So it helps us put numbers to it, and we can define a real process based on a similar but hypothetical, I guess based on a okay, so we're defining a real process based on a similar as it can be, not exactly the same because it's a different process, but we're defining this real process based on a similar reversible process. So we can define this using a concept we call isentropic efficiency, which we give the variable eta. It's like an N with a big swoopy leg. It's a Greek letter eta. And this tells us we're going to use this for work producing processes like a turbine, and work consuming processes like a pump or a compressor. And our definition, unfortunately, we just zoomed away. I don't know where we went. I don't know why that does that sometimes. All right. So unfortunately, the definition is going to change a little bit depending on the exact system. It changes in a rational way, I guess, so at least there's that, but it does change a little bit. It kind of tells us how close are we to reversible? I mean, that's essentially what it's saying. What fraction of the way are we to a reversible process, this ideal or best possible process? So for a turbine, our isentropic efficiency is the actual work that we get out of our turbine divided by the work that we would get out if our turbine was perfect, if our turbine was reversible. So how much did we actually get? Say we got, I'm going to make up numbers. Say we got 90 megawatts. That's how much work we actually got. But the reversible turbine should have given us 100 megawatts. So then we'd be 90% efficient. That's how we'll talk about it. So this is, right, this is for a reversible adiabatic turbine with the same inlet and the same outlet pressure. So that's like as close as we can get to match the two systems. That's what we're trying to do. We're trying a similar but a hypothetical ideal process compared to our real process. So we have the same stuff going in, and we don't have exactly the same stuff going out, and we'll go through an example so we can see why this changes. But we have the same stuff going in and the same pressure, at least at the outlet of our turbine. So just to get a sense of what some of the numbers would be, typical values for real systems, they're going to change with how well designed the system is. They're going to change with what operational conditions the system is working with. They're going to change with what fluid you have. They're going to change with how big the system is. So that there are a lot of variables that go into actually designing this, but it's going to be somewhere probably in the range of 0.7 to 0.88 or 0.9. So 70 to 90% efficient. That doesn't mean that, again, we'll come back and we'll talk about other types of efficiency, but this is like how close are we to the best possible turbine? Maybe 70 to 90% of the way there. We could also think of a different device that's changing thermal energy into mechanical energy, one we've talked about already. A nozzle. And in our nozzle, we're trying to change thermal energy into mechanical energy, but that mechanical energy is in the form of kinetic energy, right? So our gauge is going to be how good did we do divided by how good we could have done. But it's going to be the kinetic energy, EK actual, divided by EK reversible or ideal. right? If we went through, this would be V squared actual divided by V squared reversible. Well, 0.9 to maybe 0.97. So it's relatively easier to design a nozzle than it is to design a turbine. You might expect that because a turbine has actual physical moving parts where a nozzle doesn't. So we can get closer to our ideal case with a nozzle. The flip side is a compressor, or I'll just write it like this, or a pump. Compressors and pumps are the same basic thing, the same basic equation. And we have to think about what we're trying to do. So in a turbine, we'll say a turbine right up here at the top. What we're trying to do is we're trying to get as much, it's a work producing thing. We're trying to get as much as possible, right? So we want to see how much did we get divided by how much could we have gotten. A compressor or a pump is the opposite, because what we want in a, say, a pump is we want a certain outlet. Like, say we want it to go from atmospheric pressure to, 10 atmospheres, something like that. We want a certain change, and we want that change to be as easy as possible. So we need to put in a certain minimum amount of work to create the change that we want. And we're going to need to put in more work than that because our system is not perfect. So the definition, the equation flips for pumps and compressors. So the equation for those are work reversible divided by work actual. Because right now this is, again, it's this is the smallest amount that we could put in to get the change that we want, divided by the amount that we actually have to put in to get the change that we want. Okay, and typical values are going to be kind of in the same range that they are for turbines. Maybe 0.7 to 0.88. Okay, it's a little weird to keep track of because the ratio can flip. I'll just write eta, so it's a little bit. So the easiest way to remember is that you should always be getting a number between 0 and 1. And your real system should always be worse than your ideal system because it's the real one. So you have to kind of think in the context of this thing, what does worse mean? In the context of something that you're getting work out, worse means you don't get as much as you want. In the context of something where you're putting work in, like a pump or a compressor, it means you have to put in more than you would want. Because that's going to be, what costs you money, or what are you trying to do? So the definition flips a little bit, but it's always supposed to be 0 to 1. And you always have to think the real thing is going to be worse than the ideal. So hopefully that can help you keep track of which way the ratio goes. Does that make sense? Okay. So we'll do a quick example. To see how that goes. Let me. Okay. So this is a real turbine. So I'll give you a little bit to write down some of this stuff. This turbine has, and there are a couple things about it. So this is the inlet. It's superheated steam, 500 degrees Celsius, 500 kilopascals. And I've already gone and looked up for you what the enthalpy is and what the entropy is. And then we know that the outlet is 100 kilopascal. So we know everything that we need to know about the inlet, but we only know a single thing about the outlet. So that's a key for us to think, okay, then we must know something about the process, how we get from the inlet to the outlet. What does that look like? And in this case, we're told that it's has an efficiency of 70%. So that's kind of the key word that you should key in on. If you don't know everything about the outlet, you should say, okay, maybe I know something about the process. And being told that it operates with an efficiency of 70%, that gives you the information. We'll see how that works functionally, but that gives us the information that we need. And then we're also asked how much entropy is generated. So we'll calculate that at the end. But the first thing that we need to do is find out, like, once we find out what's coming out, then we can do our energy balances, and then we can answer the rest of the question. But that's really what we're trying to do, is find out what exactly is the state at 2. Okay, so hopefully you got a chance to write some of that down. Okay, so here in our example, we know the efficiency is 0.7. We're given that. And because this is something where we're getting work out, that means we get only 70% as much as we could. So that means that that's the work actual over the work reversible. Okay. For any of these systems, we're going to start with an energy balance. Well, we could start with a mass balance. So the mass flow rates are, the in and the out are equal, so we'll just call it the mass flow rate. It's obviously not always going to be the case. And we know from our energy balance okay, this is our general energy balance. We're going to go through and simplify that. So when we have a turbine like this, we're not told anything about, right, the enthalpy, delta H always stays around. We're not told anything specific about velocities or height. So it's generally a safe bet to assume that those are not exactly 0, but small enough that we don't have to care, right? They're a rounding error. Q is a little bit of a harder one to see always. I don't think that, so we weren't told anything specific about Q in this case. It's generally a pretty safe assumption that Q is 0 for, or about 0 for systems like this. Come on, buddy. Go to that. It's generally a fairly safe assumption that Q is about 0 for both, like, basically for work producing or work consuming things, unless you're specifically told something about Q. So we're left with the energy balance delta H equals minus W. I'll switch to black, and we can expand that as m dot H2 minus H1 equals m dot, and then the specific work, so that our mass flow rates can cancel out. So that's our energy balance. All right, so we have to, that should have a, minus right there, so that the signs all carry through, because we had a minus up here. All right, so so we have our energy balance. We need to figure out what's the actual outlet. So that we need to go back to what is the process by which we get from the inlet to the outlet, and that's we operate with an isentropic efficiency of 70%. So that's what we have up here at the top, our given. But in order to figure out this equation, we can figure out the work for a reversible process, this hypothetical best possible process. We'll figure that out first. That's always our first step in these. We'll figure out the ideal process first, and then we'll go back to the real process after that. So our ideal process our adiabatic reversible process, that's our ideal turbine. Forgot the word adiabatic. Right, this is just our ideal best possible turbine. Is a turbine where delta S is equal to 0. So we can figure out then, we would be looking for our ideal outlet. We'll call it H2 ideal, because we're only really interested in the outlet enthalpy. That's going to be at our outlet pressure. And delta S equals 0. So this is telling us that S1 is equal to S2, which is equal to, I can't remember, 8.087. So that's our outlet, and 8.087 kilojoules per kilogram Kelvin. Okay, so if we want to find our ideal outlet, we're looking up these two numbers in our tables, this pressure, this entropy, and we're trying to find what's the enthalpy at that state. If we look that up, the enthalpy is 3003 kilojoules per kilogram. So that's our ideal outlet state. So then we can go back and solve our energy balance. Right, for the ideal case, which would be H2 ideal minus H1 equals minus W. which is 3003 minus H1, which was 3484. Okay, and then we find that our ideal work is equal to 481 kilojoules per kilogram. Okay, so we've solved the ideal process. This is how much work we could get given that inlet and given our outlet pressure. But we didn't get that much. We got 70% of that. So how much did we really get? Yikes. A real turbine. So we know that 0.70 is equal to real over ideal, which gives us that the real turbine, right, is 70% of 481, which is 336.7. kilojoules per kilogram. So that's our real system. But this is only getting us part of the way there. This tells us how much work we got. We can think about, okay, what's like physically happening, and right, you're taking an inlet that has some amount of thermal energy, and you're removing that to convert it into work. But because of conservation of energy, because the energy balance still works, we can find the real outlet with an energy balance, just like we've used energy balances in before. So this just means in the ideal case, we could kind of suck out 481 kilojoules per kilogram. And that would be the best that we could do. In this case, we're only, we're only sucking out 336.7. So the thermal energy that we didn't get is still there. So we can find our real outlet. We can find our real outlet from the energy balance, H2 real minus H1 equals minus W real. So this energy balance, whether it's the real turbine or the ideal turbine, that energy balance is the same and it works the same. So we could find H2 real equals H1 minus W real, which is equal to 3484 minus 336.7. That would all have units of kilojoules per kilogram. So the enthalpy left over at our outlet is (3147.3 kilojoules per kilogram. Okay. Right. So in this way, right, flip back to the problem. So we had this real inlet. we could figure out the ideal case, and we could figure out the temperature and the pressure and the enthalpy and the entropy and everything that we needed to know about the ideal outlet. Then we could go and connect it with this efficiency to get the real amount of work that we're extracting here. And then we can go back and use kind of those two pieces of information, go back to our energy balance. Now we know the pressure and the real enthalpy of this stream. So now we can, again, go back and find like entropy and temperature and everything else that we need to know about the real outlet. So we can look up, if it lets me flip back, okay. So we can look up our, the real entropy of our outlet, which would be at, right, P2 equals 100 kPa, and H2 is 3147.3. So those are the two numbers we'd now be looking for in our table, that pressure and that enthalpy. And we're trying to connect that to an entropy. We could find that the real entropy is 8.339 kilojoules per kilogram Kelvin. And then if we did things right, this should be a bigger number than the entropy going in, right? Because entropy, in the ideal case, it stays the same. In a real case, it has to go up, right? It always has to be increasing, increasing, increasing. So this should be a bigger number than what came in. That, in fact, is the case. So our real delta S equals S2 real minus S1 is 8.339 kilojoules per kilogram Kelvin minus our S1, which is 8.087. So delta S real is 0.25 kilojoules per kilogram Kelvin. So because this is positive, it means we obeyed the second law. Things check out. We didn't break physics, or we didn't break thermodynamics. We can also there are kind of different ways that we can think of it, right? Our ideal turbine outlet, the work was 481. Our outlet temperature, we didn't look this up, but I can just tell you what it would be if we had looked it up. It would have been about 264 degrees Celsius. So again, if we go back to this example, what's happening, we have high pressure and high temperature, 500 kPa, 500 Celsius. We're extracting some of that thermal energy. We're left with lower pressure, 100, and lower temperature, 264. Right, we're extracting some of that thermal energy as work. We're left with lower temperature and pressure, less thermal energy here. Our real turbine our work was 336 kilojoules per kilogram. And our real outlet temperature, again, we didn't look this up, but we could have, was 336 degrees Celsius. Again, if we think of it as this turbine is extracting some of the thermal energy, the real turbine isn't quite as good at that. So we're left with more thermal energy afterward, right? We're still at 100 kilopascal, but we're hotter than we would have been. So there's more thermal energy that we could have got, but we didn't because our turbine wasn't perfect. So that's kind of the, I guess, the conceptual way to track that. But because we can figure out, because our energy balance still works, we can figure out all of these things. Like we can figure out what the outlet enthalpy is, what the outlet entropy was, what the outlet temperature was, all for the real case in the same way that we would for the ideal case. It's a few extra steps, but we can connect all of these different dots. The last way, and this just quickly, but the last way that we'll look at this is on a pressure or temperature entropy diagram. So this is temperature and this is entropy. And I'll zoom this up, and I'm showing you this because we'll continue to look at this diagram because it will actually be pretty useful in conceptualizing what's happening when we go to larger systems. So we have this system, right? The first thing that we put on this kind of a graph typically is the phase lines. So right, this would be SF. That would be SG. Okay, if we look at lines of constant pressure, right, this is temperature and entropy here. So if you're at constant temperature, you're just moving straight across. If you're at constant entropy, you're moving straight up and down. If you're at constant pressure, the lines look a little bit weird. Kind of the whole time that you're boiling, so if you're moving from a liquid to a vapor, the whole time that you're boiling, temperature and pressure are both constant, because temperature and pressure are both constant while you're boiling. But if you boil a pot of water, it's 100 degrees until all of it's boiled. Entropy is increasing, though, as you go from liquid to a gas. So we're moving across here, increasing entropy, but constant temperature, constant pressure. And then once you turn into a gas, as temperature goes up, entropy goes up at a constant pressure. So you get lines that look like this. So this is, we'll call this P1, 500 kPa. And our second pressure, this is P2 equals 100 kPa. So these are what lines, there would be other lines. Up there. And then they have a really steep slope in the liquid regime, right? So this would be pure liquid. Then they have a super steep slope. When they're a gas, they kind of bend upward like that. And what we have happening, we're going in the ideal case, right? We're going from, say, this is 500 degrees C. We're going from there at 500 degrees C. We can think of this process as, a straight vertical line from 1 to 2, because our entropy is staying constant. The real case, our entropy is not staying constant, it's increasing, So we're going to go still from this black line to this black line, but we're going to go further to the right because entropy is going up. So this is that's our real process. It kind of bends. It still goes between the same two lines, the same two pressures, but we're bending to the right. Our entropy is increasing and our temperature is increasing because we crashed into this line higher up on the chart. So this is real. Okay, we'll come back to this kind of temperature entropy or pressure entropy picture of things because, again, it will be important as we kind of think about it graphically, but maybe this visually helps you or will help you once we see it more kind of piece together what's happening in these systems. So we'll stop there for today. I'm going to hang around here for office hours. If you have any questions on any of this or on any homework stuff, I'll be here for the next while, as long as we need. Otherwise, hope you all have a great week. Remember to take the quiz today. Shoot me an email if you have any issues with that. So have a great week, everybody.